And there is another special basis we call an orthonormal basis. So we know that every vector space always have a basis. Every vector space always have a basis. But in inner product space, we always have a special basis called an orthogonal basis. In this theorem, the Gram-Schmidt theorems, this theorem tells how we construct an orthogonal basis from a basis from any basis. So it says that suppose that we have a mutually orthogonal W1 until Wm. This is a mutually orthogonal, and all these vectors are non-zero vectors, and these vectors is the element of an inner product space. So this is a vector space together with an inner product. If y is in a vector space P, and we can compute Wm plus 1 is equal to y minus the sum of these terms, the sum of the dot product of y and wj of the inner product of wj and wj, and we multiply by wj. So if we compute these vectors and we collect together with W1 until Wm, then this new set of vectors are mutually orthogonal, and the span of W1 until Wm and y is equal to the span. So the linear combination of the first one will equal the linear combination of the second set. Okay, I will give an example how we construct an orthogonal basis from the formula in Gram-Schmidt theorem. And this theorem implies that any finite dimensional inner product space V has an orthogonal basis. Also, any finite dimensional inner product space has an orthonormal basis. The difference with orthogonal and orthonormal just the norm of the vectors. In an orthogonal, it is not necessary to the norm equal to 1, but in an orthonormal basis, the norm of the base vector in basis must equal to 1. Okay, I will give an example of how we construct an orthogonal basis from Gram-Schmidt theorem. Okay, this is the example of Gram-Schmidt theorem. Gram-Schmidt, Gram-Schmidt. Okay, Gram-Schmidt theorem. Okay. Now we consider a vector space, a subspace. We take a subspace of R4, the vector space of the dimensional 4. R4. And we call it V, subspace subspace V of okay. What is the subspace? The subspace have three vectors, have a basis with three vectors. So we have a subspace pair uh, with basis is so we directly give the basis a basis of a subspace of V. We don't need to prove this is a basis. So, oh, sorry. So the first factors. Sorry. The first factors. Okay. So the first factors is 2, 1, 0, 2. The second vector is 0, 1, 1, 4. 0, okay, I just copy this vector. Second vector is 0, 1, 0, 1, 4, and the last vectors is 3, 3, 3, and 0. So this is the a basis of V. We can check that this basis linear. Sorry, this set is linearly independent, but because this is a subspace, so V the dimension of V is 3 because we have 3 factors in its basis. Okay, we also have the R4. We know that R4 is an inner product space. Inner product space is an inner product space. So this vector space has an inner product. What is the inner product? Its inner product. The inner product is the usual dot product for so we have uh, a dot product, a dot product as an inner product in R4. So the dot product is also an inner product in a subspace P. Because this is an inner product space, we want to construct an orthogonal basis of phi, but this basis is not orthogonal because if we look the first and the second vectors, the dot product is not zero. If we compute the dot product, so let this set B. We can check that B is not an orthogonal basis. So B just a basis, but not an orthogonal basis. Why? Because the dot product, the first and second vectors is not equal to zero. Since the dot product, so if we compute dot product of since the following dot product is non-zero. Okay. The dot product between the first and the second vector. So if I write the dot product between the first and the second, we compute the dot product, and this is 2 times 0 plus 1 times 1 plus 0 times 1 plus 2 4. So this is the usual dot product, and we get this is 0 plus 1 plus 0 plus 8. So the dot product is equal to 9, and this is non-zero. This is non-zero. Because an orthogonal basis is to every pair of two, the dot products always zero. That's the definition of an orthogonal basis. But we have the dot product between the first and second vectors is not zero. So this is not an orthogonal basis. D is just a basis, not an orthogonal basis. So how we get how we obtain an orthogonal basis? So we can produce an orthogonal basis from B using the theorem of Gram-Schmidt, the Gram-Schmidt theorem. So we will construct an orthogonal basis from B, an orthogonal basis from B using Gram-Schmidt theorem. Using the formula in Gram-Schmidt theorem. I will copy the statement of Gram-Schmidt theorem. So this is Gram-Schmidt theorem. This is Gram-Schmidt theorem. We will use this formula to obtain a mutually orthogonal set, a mutually orthogonal basis. Okay, so what is W1? What is the first factors in mutually orthogonal basis? Our purpose to get the orthogonal basis, an orthogonal basis. So we can let the first factors, the W1, that the W1 is equal to B1. Okay. The first factors in basis B. So, okay. So suppose the B1 is the first factors. Okay. B1 is the first factors. Sorry. Sorry. Okay, and B2 is the second factor. B2 is 0, 1, 1, 4, 0, 1, 1, 4, and B3 is the last factor, the third factor. Okay, now in Gram-Schmidt theorem we have a set of a mutually orthogonal set from W1 until Wm. So what is W1 in our example? We can set W1 is the first factors or the second vectors. We can also choose the second vector. We can also choose the third vector. But so the W1, the first factors in our mutually orthogonal our orthogonal basis is V1. Just take the first vectors. So W1 is 2102. Jadi W1-nya boleh pilih salah satu dari vektor yang B ya. You can choose one of the vectors in B for the W1. Okay. Because only one, we only have one vectors. The set of one vectors is automatically orthogonal. Okay. And then what is the W2? Yeah. Okay. So what is W2? W2 we obtain from this formula. So in this formula we have y. So what is y? Let y is V2. Let y is V2. So let y is V2. Then because we only have W1, so next we want to get the W2, the second vectors in an orthogonal basis, in our orthogonal basis. So W2, now M equals only 1, equals to 1. So Wm plus 1 is W2. W2 is equal to y, okay, y minus sum of these terms of vectors, because m on is equal 1, so this is only one terms. So we get this is the fraction of the dot product. Okay, the dot product okay, the dot product between, okay, look the formula, the dot product between y and wj, w1, because j start from 1. Y and W1. And this is the dot product of W1 between W1 and itself, W1. Okay, times W1. So because m is equal to 1, so we only have one terms. Jadi kita cuma satu bentuk ya, satu vectors ini aja ya. So this is the formula if for m equals 1. Okay, now we compute y is 0,114, so minus Now we compute the dot product y and w1. Y, so this is between fit the dot product between first and second vectors. First, we already compute this the dot product. So the dot product is 9. This is 9. Uh, 9 of what is the dot product? W1. W1 is P1. So this is 2 squares plus 2 squares plus 1 square plus 0 plus 2 squares. 2 squares. And we multiply this fraction with W1. W1 is P1. We simplify the second terms. This is sorry, 0114 minus 9 of 4 plus 1 plus 4, 9. Right? 4 plus 1, 4 plus 1 plus 4. 9. Is this right? Betul ya? Okay. So we just subtract P1 and P2. This is P1 minus, oh sorry, this is P2, P2 minus P1. P2 minus P1. P2 minus P1, and we get, okay, what is this? Vectors. Okay, this is minus 2, 0, 1, and 2. So we get W2. Now we have two factors. Two factors with is mutually orthogonal. So we have now we have mutually orthogonal. Mutually W1 and W1. Now W1 and W2 are mutually orthogonal. Or it means that the dot product of W1 and W2, now dot product is equal to 0. The dot product is 0. So if we check W1 is 2100 is 2102, and W2 is minus 2012. Now W1 and W2 are orthogonals, so the dot product is 0. You can check. This is minus 4. 1 plus 1 times 0 is 0. 0 times 1 is 0, and 2 times 2 is 4. So and we have 0 in their dot product. Okay. So in the first steps, we only W1 and then we compute W2 from this formula. Now we have two factors which are mutually orthogonal. Now we continue the process to get the W3 because the basis of a V always have three factors. So an orthogonal basis of V also have three factors, but now we have two factors, so we compute again for W3. So what is W3? From the formula, we get W3. So M now is 2. W3 is, and we update the previous iteration. Y is D2 now in the third iteration. Y is P3. So we substitute Y with P3 now. Y, this is the sums. Y minus the sums. Okay, the sums. The sum from J equal to 1, from J equal to 1, and until J equal to M. But now we have M is 2, because this is W3, Wn plus 1, and M plus 1 is 3, then M is equal to. Okay, the terms in the sum is sorry. Okay, so this is Y WJ, this is WJ, WJ. So what is the sum if we expand this sum? So this is Y minus we just start from J equal to 1. We substitute J with 1, 1. This is 1. This is 1. Plus J start from 1, 1. And sorry, this is marking bracket. Because sum is terms 1 plus terms 2 plus J equal to 1. Okay, so this is the sum. Okay, and substitute from the formula. Okay. Okay, now let W is P3. W is P3 and Y is P3 and W3 is this one, and we compute W. Sorry, y is P3. P3 is this. Okay, minus. Okay, this is the sum of two factors. The first factors we already compute in the previous process. This is we just substitute. Okay, this is minus the first one is A, and the second one is we must compute. Oh, sorry, this W2, all W2, because J equal to. Okay, now compute W2. Well, W2 is minus 2012. This is minus 2 square plus 0 plus 1 square, 0 squares plus 1 square plus 2 squares. And what is the product of the y and w2? Y and w2. This is y, P3. Y is P3. Okay, y is P3, so the dot product y and w2 is 3 dot 3 dot minus 2, 3 dot minus 2 plus 3 times 3 dot 0 plus 3 dot 1 plus 0 dot 2 multiply with W2. We calculate in the second bracket. Okay, this is minus. I just open the bracket. Minus, and this is minus. Okay. Now plus 4 plus 0 plus 1 plus 4. 4 plus 0 plus 9. And on the top fraction, 3 minus 6 is minus 6 plus 0 plus 3 plus 0. So minus 6 plus 3 is minus 3. Minus 3. Because this is minus, and minus is plus. Multiply with W2. Okay. Okay. Okay, 3 minus 2 minus 2 of third, 2 of third. Okay, and then 3 minus 1, 0. 3 minus 1 plus 0. 3 minus 1 plus 0. Okay. 3 minus 0 plus 1 third. 3 minus 0 plus 1 third. 0 minus 2. 0 minus 2 plus 2, 2, 2 thirds. 0 to 6. Okay. So what is W3? W3 is equal to 1 third. One minus 2 third is 1 third. 3 minus 1 is 2. 3 plus 1 third is 10. 10 third. Okay. Minus 2 plus in 2 plus 2 per 3. Berapa tuh? Minus minus
4/3, Pak.
4/3 ya? Okay, so this is W3. And we now have three factors which mutually orthogonal. So we now have W1. W1 is okay. W1 is 2, 0, 1, 0, 1, 2, and W2 is and W3 now. So these three factors are mutually orthogonal. Which means the product between 1 and 2 is 0. The dot product between 1 and 3 is 0. The dot product between 2 and 3 is 0. So each pairs of vectors are orthogonal. So we call these three vectors are mutually orthogonal because we obtain the mutual orthogonal from a basis. Then these three factors, let's say B1 is W1, W2, and W3. Now this set is an orthogonal basis. So that's the Gram-Schmidt process. So Gram-Schmidt process, the purpose of Gram-Schmidt process is to produce an orthogonal basis from an ordinary basis or from any basis. So in the first, we have a basis of B. Now we have an orthogonal basis of subspace B. Okay, so that's how we compute an orthogonal basis. From orthogonal basis, we can continue to produce an orthonormal basis. From orthogonal basis, we can construct an orthonormal basis. Orthonormal basis. So how we get an orthonormal basis? Oh, okay. The process only normalize its factors. So we normalize its factors. We normalize each factors in basis. Each factors in basis. What is the what? How we normalize or what is normalized vectors? Normalized is we divide with its norm. So we from W1, okay, this is W1. This is W1, okay, and then we compute the norm of W1. The norm of W1 is the symbol of norm is double bracket. Sorry. Okay, double bracket. So the norm of W1 is the square root the square root of 2 squares plus 1 squares plus 0 squares plus 2 squares. 4 plus 1 plus 0 plus 4 is 9, so the square root is 3. And we normalize, so we divide W1 with its norm. So this is okay, or because norm is 3, so we get 1/3 of W1. 1/3 of W1. Okay, so this is the normal. We already normalized the vector, the first vectors in orthogonal basis. We continue for W2. We normalize W2. First, we must compute its norm. W2 is -2, so this is so the norm same because only different negative in first coordinate. W2 also the norm is also 3. We divide the vector W2 with its norm. Okay, and we get this one. but in the first column we put minus to term. Okay, this is the normalization of W2. And for the last one, W3, we compare its norm. The norm is W3. Oh, okay, 1/3 is 1/3 squares. Okay, 1/3 squares and 2 squares. This is 2 squares. 10/3 squares. 10/3 squares plus one is minus 4/3 squares. Okay. And this one is 119 plus 4 plus 109 plus 16. Okay, I will calculate this one. 19 plus berapa nih? One hundred 17 plus 36. Ya.
17, Pak.
Benar nggak?
Akar 17 maksudnya.
Yeah, still in square root. Square root itu square root 153 ya. Per
9.
ya, benar. Square root 9 is 3, so I keluarin.
Itu 153 bisa dibagi di 9 sih, Pak.
Oke. Sorry.
Jadi
Bapak
17.
kayaknya salah taruh akarnya deh. Apa itunya pembagian.
150 is a multiple of 9.
Iya, Pak.
Oke. 153 kelipatan 9 nih. $150 is 9 with
Bapak,
17, Pak. 17.
Bapak, itu bukannya
Sorry, ya. Kenapa?
itu bukannya 153 bagi 9 baru diakarin ya?
Iya. 153, 153, 9. But 153 is multiple of 9. Yeah. We can divide by 9. 153 is 9 kali berapa?
17, Pak. 17.
Bro?
17.
Oh, 17. Oh, okay. 17. So, square root of 7. Okay. So this is the norm of W3, and we normalize by we divide W3 uh, with its norm. Or this is equal with 1 square root of 17. W3, W2, okay. Okay. Or oh, sorry. One. Yeah, okay. I just put. I don't want to compute this one. So we get an what is the orthogonal basis from B1. So I just say let this the new basis is B2. B2 is normalization of W1 is this. Okay. This is normalization of W1, and this is the normalization of W2. And this is the normalization of W. Okay. Now B2 is an orthonormal basis. What is orthonormal basis? Means this basis is an orthogonal, but every vectors has the norm of every vectors is equal to 1. So the norm of this one is 1. The norm of the second vector is 1. The norm of the third vectors is also 1. And in the dot product between two vectors in the set B2 is always 0. So this is an orthonormal basis. So from this example, we always we can always construct an orthogonal. We can produce an orthogonal basis from an ordinary basis, and we can also produce an orthonormal basis from ordinary basis, from an orthogonal basis. Okay, any questions for Gram-Schmidt process? Ada pertanyaan nggak? Any questions? Ada pertanyaan? So from Gram-Schmidt theorems, the conclusion is this theorem. So the existence of orthogonal basis, any finite dimensional inner product space, a product space that has an inner product always has an orthogonal basis and hence an orthonormal basis. Okay, any questions for Gram-Schmidt process? Okay, now next we look what the properties of an orthogonal basis. So, if we have any vector Vn in any vector space V, let's say V is any vector in V, and then we also have an orthogonal basis U1 from U1 until Un. Because U1 and Un is a basis, so V is a linear combination of with respect to this basis. So V equal to A1 U1 plus A2 U2 plus blah 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 and A1 B1. And what is the scalar A1 from An? The scalars just compute the dot product, the inner product between V and UI. So A1 is the dot product V U1 and A2 is the inner product between V U2 and A3 is the inner product of V with U3. So to get the scalars in the linear combination, we just compute the inner product with V with the orthonormal basis. Oh, sorry, this is the properties of an orthogonal basis, how we compute or how we know the scalars in this linear combination. If U1 and Un is an orthogonal basis, so the scalars is the dot product, the inner product between V and the vectors in basis. Okay. For example, okay, so okay, this is Gram-Schmidt procedure. So we already use this procedure. Okay. So the example is so I will give an easy example for to show the properties or the special condition or special okay. So consider the vector space, I just give a vector space in R3. Okay. We can just put R2. So one of orthogonal basis of R2 is the standard basis. Standard basis Standard basis is an orthogonal basis. Orthogonal basis. What is standard basis? Standard basis is 1, 0, and 0, 1. 1, 0, and 0, 1. And 0, 1. Zero, one. Okay. Oh, sorry, this is an orthonormal basis also. This is, orthonormal because its norm is orthonormal basis. And R2 has a dot product. The dot product. Dot product. Okay, if we take any vectors, let's say any vectors 1, 2. If we take 1, 2, any vectors, for example, if we take 1, 2, okay. So how we write this linear V as linear combination 1, 0, and 0, 1. This is A1. So this is A1 plus A2. Oh, sorry. A2 okay. How we find A1 and A2? But for because 1, 0, and 0, 1 is an orthonormal base, we can find A1 from the inner product, the dot product between V and 1, 0. Okay. So just compute the dot product between P and 1, 0, and A2 is the dot product between this is the dot product V with 0, 1. 0, 1. Okay, so V is 1, 2. V is 1, 2. Okay, this is 1, 2. Okay, and the product is 1, 1.1 plus 2.0. We get 1, and A2 is 1.0 plus 2.1, so we get 2. So A1 is 1 and A2 is 2. So this is how we find the scalars if the basis is an orthonormal. Okay, just compute the inner product between the vectors and the vector in basis. Oke, jadi kita langsung bisa mencari scalarsnya langsung dari dot product ya, nggak usah kita cari linear systemnya ya. Okay, we don't need to solve the linear systems to find A1 and A2, but you can just compute the inner product. You will get the scalars. Okay, this is the special properties from orthonormal basis. Okay. How we get scalars? We compute the dot product. Okay, any questions for orthonormal basis? Any questions? Maybe this is not a good example to show the properties, but you can choose any orthonormal basis, but not standard basis. And this properties also satisfies for any orthonormal basis. Oke. Okay. Jadi mungkin contohnya nggak terlalu menarik ya karena 10 pasti udah tahu ya. A1 pasti 1, A2 pasti 2 gitu. Tapi kalau kalian pilih orthonormal basis yang lain itu langsung pasti susah ya kalau pakai linear system. Nah, kalau kita hitung pakai dot product itu pasti langsung ketemu, lebih cepat lah. So it's easy to get the scalars from orthonormal basis in its linear combinations. Okay. Any questions for orthonormal basis or orthogonal basis or Gram-Schmidt procedure? So the main result, the main one main properties of an inner product space, this vector space has an orthonormal basis, has an orthogonal basis. Okay, next, after we study about orthogonal basis, next we will see that the scalar in linear combination of bases is unique, are unique, the scalars are unique with respect to the basis. Jadi scalar untuk linear combination yang ada di basis itu pasti tunggal ya. Jadi satu V satu sequence scalar, satu basis satu sequence scalar. Berikutnya itu adalah tentang coordinates ya. Jadi any vectors in vector space, it can be vectors, it can be matrix, but all vectors can represent by a coordinate. So the next topic is about a coordinate of any vectors. So any vectors always have coordinate, just like R2, R3, R4. Okay. How we get the coordinate? The coordinate is obtained from the scalars in linear combination. So, okay. So now we talk about a coordinate with respect to a basis. So a coordinate based on this theorem, based on a unique sequence of scalars in the linear combination. So suppose that this basis P1 until Pn, this is suppose that this is a basis, then we know that every vectors uh, can every vectors is a linear combination of the basis, okay? Or we can write W, this vectors W equals A1 P1 plus A2 P2 blah 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 plus A1 P1, and the scalars is unique. It means the solutions only get one answer. So we only get one scalars for A1, one scalars for A2, and one scalar for AN. So it means a unique sequence. It means there is no other sequence. There is no two sequence for this linear combinations. Okay, because the sequence of scalars unique, we now consider an ordered basis. A sequence always considered as an ordered collections. So now a basis also we can also consider an ordered basis. Okay. An ordered basis is a basis whose elements are listed in specific order. So now if we take a basis, let's say 1, 0 and 0, 1 in R2. If this unordered basis, then 0, 1, 0, 1 and 1, 0 is a different basis. Okay, this is different because now we look the order, we look the because the factors list in a specific order. So in the first basis, 1, 0 is the first one, but in the second basis, 0, 1 is the first one. So this is different in order basis. As an order basis, this is two different basis. Okay, so from an ordered basis, the scalars, the sequence of the scalars is also has unique order. Okay. So if we have an ordered basis, so the unique sequence of scalars, this is the coordinates. So the coordinate means the coordinate is from the scalars in linear combination. So if W is any vectors and this is the linear combination with respect to an ordered basis, and this is the coordinate. What is the coordinate? Every component from the scalars. Okay. So for example, let be an ordered basis in R3. So this is not a standard basis. Okay. This is just ordinary basis, but now we see B as an ordered basis. Okay, so the first one must these vectors 1, 0, 2. Okay, if we write 3 to 6, The first one is 3 to 6. So this is not B. So this is different with B. If the first one is 3 to 6, 1, 0, 2, 2, 1, 5. So that's another basis different with B. Okay, because now a basis the factors is list in a specific order. And then we ask what is the coordinate of vectors 1, 1, 1. But this vectors is already in coordinate. No, because we ask this coordinate with respect to the B. Okay, so this is not the coordinate with respect to the B. 1, 1, 1 is a vectors. We consider it as a vector. 1, 1, 1 is a vector, but the coordinate is we must find the scalars from the linear combination of the. Okay. So we get the scalar is 0, 1, minus 1. So the coordinate with respect to the B is 1, 0, 1, minus 1. So this is the coordinate with respect to the B, not 1, 1, 1. Okay, and we write the coordinate like this, 1, 1, 1, and B as an index. So we read this, the coordinate of the vector 1, 1, 1 with respect to the B, with respect to the ordered basis. What is the coordinate? 0, 1, minus 1. Ada pertanyaan nggak? Jadi vektor itu punya koordinat terhadap basis ya. Jadi kalau 1, 1, 1 itu bukan koordinat, ini kita anggap vektor. Tapi koordinatnya terhadap B itu adalah 0, 1, minus 1. Okay. But if we consider another order basis, like 3 to 6, yeah, 1, 0, 2, 2, 1, 5. Okay, this is a different basis, different order basis, and the coordinate. Sorry, let's say this one is B1. Okay, the coordinate of 1, 1, 1 with respect to the B1 is, because the first one is 3 to 1, the scalars must 1, 1, 0, minus 1. Okay. So the coordinate now different because we have a different order basis. Okay. Okay. And the coordinate, just like coordinate in R2, R3, if we sum and if we multiply by scalars, and we can just see like the sum of vectors, the sum in coordinate, and scalar multiplications in coordinate vectors. This is just the properties, one of properties. Okay, this is how we change the coordinate of one vectors from one basis to another basis. We call change of basis. So suppose that B1 and B2 are two ordered, then we can change the coordinate from B1 to B2 by multiply a matrix, an invertible matrix. So we can change by multiplying the coordinate by a matrix, an invertible matrix called P. Okay, I think we'll end this session because we already finished. Okay, is there any question before I close the session? Ada pertanyaan nggak? Jadi mungkin nanti kita coba lihat contoh koordinat dan change of basis. Any questions? Okay, no. Okay, I will finish this sessions. Thank you very much for your attention and your attendance and your participation. See you next time. Sampai ketemu lagi ya. Selamat siang. Good afternoon.
Terima kasih, Pak.
Terima kasih.